Thank you very much. It's a pleasure to be here. Today's talk is on black box approximate taint tracking utilizing data partitioning. It's quite a mouthful, but hopefully it's be interesting to you. Some introductions before we begin. My colleague Aaron, would you like to introduce yourself?
Hi, I'm Aaron Goldman. I spent 10 years doing information security at Georgia Tech. Had a brief stint doing security at Google, analyzing malware. And now I am working at T-Cell on application firewalls. So if you have an application, come see our booth.
Hi, and I'm Boris Chen. I'm co-founder and VP of engineering at T-Cell. Past companies I've been at include Splunk, and also director and engineer at WebLogic and JRocket divisions of BA Systems. So we'll just get right into the talk. First of all, I want to talk a little bit about runtime AppSec technology. So a lot of time when we talk about tools for AppSec, a lot of things that people have focused on are things like scanning tools or testing tools or code analysis tools. And those are all excellent things as part of a comprehensive application security program. However, historically, runtime security has been, I would say, underemphasized. And if we look at the technologies that we've used in the past and present as well, WAFs are the most well-known and traditional approach to runtime application security. Just as a show of hands, how many people have heard of WAFs? Okay, most people. How many people use WAFs? Okay, a few less. Another technology that's emerging right now is a technology called RASP. How many have heard of RASP? Okay, almost as much as heard of WAF. How many use RASP? Okay, no. Okay, there's a few hands there. Okay, great. So you can sort of see the difference is that WAFs are what's well known, what the industry has been reliant upon for runtime security. But RASP are emergent, and why is that? Well, before we get into that, let's talk a little bit about what is RASP. So RASP was coined by Gartner. It stands for Runtime Application Self-Protection. They say it's a security technology that is built or linked into an application or application runtime environment, and is capable of controlling application execution and detection and preventing real-time attacks. And the emphasis of mine, the detection and preventing of real-time attacks. And that's been the focus of RASP, and that's why there's been a lot of interest in RASP. And why is that? So there's a lot of opportunities that RASP provides. Being inside the app, it differs than being on the network like a WAF. And how's that? Well, you're not limited just to what's going across the wire as far as the HTTP protocol. You also have not only the same visibility into what's coming across the wire, but you also have what the application is doing code-wise and with the data. Okay? So in theory, you can do all sorts of things in a RASP because the sky's the limit. Just look at what's happening. But the reality is that there's lots of limitations, namely that if you're going to be in the runtime, if you're going to be in production, you can't take all the time in the world to figure stuff out, and you can't slow down the application, you can't impact the application in any way. You can't do it performance-wise or logic-wise. So, and also not all logic is inside the application, especially when you're talking about microservices. There's callouts, and there's lots of dependencies that go across the entire stack. So those are some of the constraints that we have and opportunities as well. Taint tracking is a technique that we'll go more into, but it's a technique that is open to RASPs that aren't open to other approaches. And it's one of the many techniques that RASP can leverage. But then in order to leverage it, we need to answer some essential questions. One is, what is taint tracking, which we'll go into. Why isn't everyone doing it right now, right? Traditional taint tracking has been around for a while. Why is that? And then what can be done instead of past approaches? So
All right, so I'm going to take you through a brief history of taint tracking. Mainly, I'm trying to cover why is it would you want to do this taint tracking, can we actually accomplish this, and why is this not going on? In any security talk where we talk about injection, it is mandatory to invoke the great Randall Monroe and his Bobby Tables character. Obviously, the problem here is that if you fail to sanitize your data inputs, some mom is going to exploit your student database and delete all of your data. But that's not the only dangerous input type. People have talked recently about, are you sanitizing your inputs? Are we serializing things well? Are we deserializing things well? Why is it that all of these serial formats turn out to be attacking your application? People are like, oh, I'm going to decode YAML. How dangerous could that possibly be? Turns out, if you don't do it correctly, your YAML deserialization could be arbitrary code execution on your server. So I'm going to look at what I consider to be a simple yet non-trivial wire format, comma-separated values. It is often mistaken for the specification being the name itself. Use commas to separate your values. But it's actually a much more complicated protocol than that. We have to be careful as you are assembling your CSVs. You can't just join on a comma. You have to sit here and say, is there some kind of thing that needs to be escaped? I need to escape my commas, and I need to escape my new lines. But we did that with equal signs, and now we've run into this case where we need to escape the equal sign. It's easy to make this mistake and say, oh, C quote CC, does this need to be escaped? And the answer is yes, because it has the escape character itself in it, so we have to escape the escaping. And it's very tempting to sit here and be like, oh, look, Python is super easy. I was able to parse CSV in one line. Except this is actually a dreadful solution. If you tried to do this in a code review, it's going to come back and the person's going to be like, no, you were supposed to use a with statement in Python if you open a file. So we see here this person is specifying their username. If they put commas in their username and now you have some create user function that goes through and makes users on all of your machines and it sets their password hash and what shell they're going to use, this person just used some comma separated values in their name and now it's going to be initialized that they get root access on the box whenever they log in. So what do? Well, we build systems that escape the user input. If we know that input is tainted, we can escape it and say, okay, this thing came in, it is a string, but it's a string that is not already CSV escaped, so let's CSV escape it. But what if someone's calling your function with already CSV escaped strings? You're going to end up double escaping or not escaping even a single time. To keep track of what things have been escaped and safely serialize data, we need to know what has and has not been done. And that brings us to our taint tracking. Also, you find people who are doing the reverse. I have some particular piece of information in my database. If I have a whole bunch of time-based one-time password secrets, these aren't like normal passwords that I can hash and really protect aggressively. My database has to be able to get back that secret. So if I leak my database of one-time passwords, the person who has the one-time password secrets can now generate the one-time passwords and log in as any of your users. So it's not safe to use the same one-time password secret on multiple sites. And largely, we have fixed this by having the server pick your one-time password secret and tell it to you rather than letting you set a password. But you have to be careful. OK, so this is a server-centric string. Let's not accidentally send that to the user. Let's track whether some piece of data going to the user has been tainted by a server-only string. So how far back does this go? Who here knows who this man is? You are all, of course, correct. This is John von Neumann of the von Neumann architecture. He had a debate. He had a bunch of friends who were deciding to get together and work on this fun project out in the desert where they were going to make a nuclear bomb. And it turned out that they needed the computer to solve lots of different problems. So they would program the computer and solve a set of equations, and then reprogram the computer and set a set of equations. And von Neumann said, I've got a great idea. What if we had a computer that could store the program in the same memory where the data is. And then we could like write in this assembly language and let the computer assemble it to machine code. And everyone was like, you and your high level languages like assembly are just nothing but trouble and gonna cause confusion. But the result of that was we ended up with one memory. So now we had data and control that were mixed. We argued for a long time, with von Neumann mainly arguing we should have programs that are capable of writing programs because assemblers are awesome, and he thought we should work on compilers, and we'll see if that takes off. And the guys from Harvard were like, no, we don't want assemblers. We want to like hand reprogram our computer every time, just like you do with your calculator when you need a new function. Ultimately, we solved this argument with the no execute bit. We are going to put things in memory and say, no, this is data. It should be data and do data-y things, never execute it. By adding one more bit to every memory address in the entire computer, we have now solved this taint tracking problem of, is this executable memory or is this not executable memory? And if you are copying memory, it stays not executable. Which is why you'll notice, since we have entered the no execute bit, there has been no malware that has been written. So you may be thinking to yourself, this is a great idea, but I'm not going to add a physical bit in memory for, has this thing been CSV escaped? Has this thing been HTML escaped? Has this thing been SQL escaped? How are we actually going to track this thing? Because I don't really want to invent a new type of memory to be able to track my tainting. And there's two main tricks we use. Inside languages that have strong typing, we can just like subclass string and be like, this is an HTML string. It's free to be concatenated with other HTML and sent out. But if you ever have a string that's not HTML that you try to concatenate, then we have to figure it out. So if I'm trying to concatenate my HTML string with my SQL string, I'm going to have to know, well, what out type am I trying to get? If I run it through the converter, I can turn my HTML into SQL so I can stick it in the database, or I can HTML escape my SQL to send it out to HTML. But I need to think, escaping is not just the user. It's not, oh, this thing came from the user, therefore it's evil. That's true, but not the complete story. We want to actually say, okay, if I'm trying to make a SQL string, I need to know, has this thing been SQL escaped? If I'm trying to make an HTML string, has this thing been HTML escaped? Then someone had this great idea of microservices and service-oriented architecture, and we should like send data from one memory space to another memory space. And suddenly, we couldn't put all this information in the types because there are no types on the wire. Everyone knows on the wire, all objects are JSON. So we have to come up with more creative things. How are we actually going to encode all this taint information? The one I usually suggest is to add a metadict to the front and just say, whenever we have one of these types that came from the user and is therefore evil, we are going to encode that as a list where the first item in the list is a dictionary with a bunch of metadata, and the second item in the list is whatever the string or values that's being encoded, with the advantage that the second value can be any arbitrary nested JSON object, and your metadict will tell you how to serialize and unserialize that. So does this mean no more errors will ever occur? No, even in a system with taint tracking, you can get messed up, and you usually get messed up by interpreters. You have something that says, I want to run this data. For example, if I have a Python script on my hard drive, and it's marked as read only, no execute, but I type Python space and that file. Okay, so the Python interpreter read my Python file. I didn't execute my no execute file. All I did was read it into the Python interpreter. Surely that's safe. What's the worst thing that an interpreter could do? And the answer is it can do whatever it wants. It's an interpreter, and you're frequently going to find that we have way more interpreters on our computer than we think. In this example, I have, say, my server-only string, some cookie or something that's not supposed to be echoed back. If I have some giant if statement that goes through and says, okay, what are all the possible characters in my string? And I'm going to make a new clean string out of all the old ones. This probably shouldn't pass your code review process, but automated tools that are going through isn't going to recognize this as having propagated taint. Because you didn't make A out of the thing on the other side. You were just like, oh, if it's an A, then give me an A. So why don't we do this? We have the capacity to do taint tracking. We have type systems. We have the ability to send messages between. And the answer is, well, with taint tracking, it has to be end-to-end. If I have taint tracking through 90% of my system, and then I have one service or one library that can't handle that, I have one string database, one entry in my database that takes an int, and I'm going to lose all my taint tracking information because I don't know whether this int came from the user or came from wherever. I need to have some way of both incorporating with software that already exists out in the world and doesn't have everything made out of my special types, and yet figure out what's going on the other side. So that's when we introduce approximate taint tracking.
So approximate taint tracking. So approximations everywhere. If we looked around in industry and we see that there's a great interest in approximations in general, especially in the big data space where you want to do very complex calculations, but even with the era of big data and have lots of compute and lots of memory, you still are constrained by time. And also when things don't scale, then you have problems no matter how much resources you have behind you. So in order to do things efficiently, there's lots of interest in approximations. And approximations are there because you're trading off the complete accuracy over things for a great gain for less utilization resource-wise. And the other thing is to keep in mind is that the fidelity that you lose in aggregate doesn't really matter in reality. That in reality, that the approximations are good enough, and so you don't need a precise count if you're looking for spikes, for instance. And there's many other situations that it shows. But the main thing is that the approximations have a huge payback when they're implemented in the system. So there's several examples listed here. Count distinct, hyperlog-log is the algorithm of choice. Quantiles, correlations, counts, element being a member of the sets, similarity matching. There's more. There's many of these. And the main thing is that all these things have a common theme in that you're trading off some fidelity in order to address the problems of the real world, which is you have real constraints that you have to deal with. And the trade-off, in effect, is marginal compared to the gains that you get by choosing an approximation. So that's when we were inspired to say, okay, how about applying the same thing? What's the approximation technique for the area of taint tracking, which also suffers from the same problems that these other approximation algorithms are meant to solve? And so the answer is we can approximate it.
Okay, so let's assume we can't do a full-on taint tracking, but we want to get a decent approximation. How are we going to go about this? Well, our proposal is exist at runtime. The compiler really wants to have these types to track where is every possible place that some piece of data could flow. But at runtime, we have the advantage that we can just look at the data. I can hook your server and say, I'm going to stick a tap and look at what's coming in over HTTP. And I can stick a tap and look at what's going out to your SQL database and say, okay, I have some application. Let's treat my application as a black box where I don't have to know all the details of the application, a mode I like to refer to as the ops guy, and see, can we tell whether you're actually getting your data tainted? So in my example, I have someone who's doing a simple SQL injection. They've specified their email address, and for their password, they have done the or 1 equals 1. So when it goes to do the comparison, it's going to say, OK, I have someone with this user, and either the password is right or 1 equals 1. 1 equals 1 is true. Oh, congratulations, you've just logged in as that user. So we can divide this up and say, all right, well, what is the actual partitions that exist inside each of these formats? So I can look at my JSON and pull out what my fields are and look at my SQL and say, OK, I can parse the SQL and know exactly where is my user data and where is my control data. This is sort of the equivalent of that Harvard versus von Neumann architecture. We have a memory that came in this case, a JSON object, that mixed control and data, and we pulled it apart and said, okay, which parts of this are my control and which parts are my data? Once I have the data, I've come up with this question of, can we tell which parts of the outgoing data came from the incoming data? And the easiest way to approximate that is it the same data? I can take some particular segment size and split my strings into that segment and say, okay, are there any of these little 5-character long chunks of my input data actually showing up in my output data in the segments? And if I've reached a situation where it's showing up in more than one, here I have what was one input, my password or 1 equals 1, but it's showing up in 2 separate partitions of the output. It's both setting the password and it's in this OR clause. Now I can say, yes, this is an injection. I have data, and then some control happened, and then my data has appeared again. Clearly, there was some amount of control that was inside of that data. And you have some kind of injection. And this can be a situation that you alert on, or if you're really in the application, you can even act on and say, I think that this input is sketchy. I'm just not going to allow this request to go to the database. I'm instead going to notify some operations person to be like, hey, I'm seeing this weird behavior. And this is an approximation, but it's tunable. If we went to very small sizes and say, okay, if there's even a single character shared between an input partition and an output partition, you're going to get a very high false positive rate. Everything's going to look like it was tainted by everything else because it's like, oh my goodness, you also used the letter E? Clearly, you've been reading my data. If I make the window very large, I'm going to get way fewer false positives. Oh, look, the same UUID has appeared in the input and the output. That is unlikely to have happened spontaneously. That is almost certainly a taint. But by making the window that large, we're now going to miss things. A short password might go right through, and I'm not going to realize it's tainted if my window's too small. So my main summary is you can tune these approximations to say, how close do you actually want to make sure that something is tainted? There are interpreters all over the place. There's things that you don't realize are reading your code and going to interpret them. When you look at a YAML file, you think, oh, this is deserializing an object, not this is arbitrarily creating Lambda calls. And that escaping is context sensitive. You really need to know what's coming in and what's going out, and does this make sense? If I have something that is inputting JSON and outputting SQL, if I can know what those 2 strings are and parse them into their various segments, I can get real strong information of which of these segments have tainted which of the other segments, or even injected it, so that I can have outgoing strings say, nothing goes back to the user if it has been tainted by a secret field, and nothing is going to come into my database if it contains an injection.
So just a recap on some of the applications and implications of this. This is excellent for injection detection, as we walked through just now as an example. But it also is good for data exfiltration, which we didn't cover, but it's something for a future talk. And then the other thing it's useful for is user privacy. So this is a very, sorry, that's not showing up there, that's good. It's a pop-up. It's a very powerful technique. We're really excited about that. We didn't get a chance to do our demo because of machine issues, so I apologize for that. But on the slides, there is a gist link, and so if you want to, yeah. So at the very bottom of here, you can't really see it, but it'll be on the slides after the presentation, and you can see this. What's that?
We should have made it bit.ly.
Yes. We'll have the source available for the string matching algorithm. So with that, thank you very much. Really appreciate you attending our talk, and we're open for questions.
Do they need to go to a mic or? We have a mic runner. Even better.
I'm one of these really old guys who started out web programming with Perl and CGI. And one of the first things that I realized was really valuable, and this was like back in 96, 98, something like that, was the Perl Tain't tracking. And I'm surprised that I think only Ruby, the only more recent language basically that I've seen, supports taint tracking. What is your opinion of why it's not more common in programming languages? Because this doesn't seem to be really that hard to support.
So here's a library for Java and a library for Python that enable taint tracking inside the VM if you would like to do things similar to the Perl taint tracking method. It has been used, but is occasionally problematic because as you are modifying it, like, yes, the VMs are actually much more dynamically typed than the languages we tend to be running on top of the VMs, and you can just stick extra metadata about any object onto that object and follow it around. But you would be surprised how often you get some random deep copy or something that causes you to lose tainting as an object is going through. So you tend to run into these, there's some small interpreter in the middle that is severing your chain, and many of those have been explicitly addressed in these libraries. So if the thing you literally did was like object.deepCopy, they're going to have addressed that one, but there tends to be a lot of flavors of that. And I think it hasn't taken off largely because people just have trouble with the implementation and keeping track of where objects are actually going through their libraries. You do still have to have some understanding of what is going on inside your libraries. Yes, if you write in, say, Clojure, for example, Clojure objects or the EDN serialization has the ability to add metadata to any object, and
Because
that
like
tends
when
to
I
track
was
much
using
better.
this with Perl, the most common mistake that I saw my fellow developers using is the way that we untaint something, dot star, okay, it's untainted. It does no good, but at least, that was something which was fixable, and it's easy to hunt down, so.
Yes, the hope with taint tracking is that you're going to have nice, clean places in your code where you're explicitly casting string to SQL string, and you can actually do an audit that says, I'm going to go look at every place in my entire code base that I cast string to SQL string and make sure that those are all words like select and where, and not here's an arbitrary string that came from the user that I'm now going to declare to be valid SQL.
More questions?
Have you done any experiment on what's the optimal window size for matching two different inputs, and in terms of low false positive, and of course high true positive?
So I don't have anything that I have statistical confidence in, but in my personal experience, when I have used 5, that tends to be fairly consistent to me. You want something that is somewhat shorter than most of the passwords in your system and credentials, and usually when you are leaking a piece of information that is significantly smaller than that, it's not some direct, you already have a direct object reference problem where someone's going to enumerate all of your secrets when they get too small. So for things like you're leaking UUIDs around, UUIDs are fairly long, and even something like 16 will tend to follow them. And having that big of a window, you're going to have very low overhead on your system. But if you really want to track things like SQL commands, there's just a lot of things that are 5 characters.
Well, first of all, I think, thanks a lot for the talk. I think this is absolutely a promising idea. But I have a question regarding some of the approximation technique you're using. For example, one of the example you show is that for SQL injection, You're trying to see that if there's one input comes in that goes into multiple outputs, that could be possible injection types of attacks, right? But for modern applications, especially web applications, it's trying to become more intelligent, right? So it's trying to guess what the user input is, and probably take user input in a kind of gross way, so that at the back end, it will try to parse the data. For example, you have full name that come in and it goes to the database. It can become first name, last name, middle name, right? Address, it comes in as the full address, and the application is trying to intelligently parse it, and then goes out into multiple data fields. So how do you kind of reconcile those kind of scenarios?
So for things like, you will often have a field that comes in that's like query.
Right, exactly.
And query tends to be very free form. And if you have explicit things that parse on your query, anything that has user colon and then a UUID is going to be parsed in explicitly that way, you can use the black box tainting on the thing that's parsing your queries. But for just generally looking at it, you will tend to just be whitelisting something like query, because for something like Google, the chances that there is a Google search that you can put in that Google is going to interpret as, I should totally run this piece of shellcode that's in your query,
Right.
seems less likely to me unless there's something sort of catastrophically wrong there. Most of those things I expect to come out of hardcore, there's a rule, if you see this thing colon, then that is a specific command that's within the query, and then those themselves become parsers that you can try and taint track on.
Yeah, I was just thinking, maybe another idea would be somehow if you can partition not only the data, but also the memory, so that you can establish some sort of control within the memory, so that maybe you can, related to what you just said, maybe there is a way you can basically put the ISP engine not only in front of the input output, but also inside the application. Like you have checkpoints inside of each application.
Yeah, if you have a runtime, you could put this
Right.
on the call and return of a function or various other things that you can get at. That would be very hard if you were trying to build a runtime around like C to do that, but
More questions?
yeah, we're the last talk. We got lots of time.
We have a keynote.
Yeah, they don't need to go to the keynote. The keynote will wait. We have the room.
Earlier you mentioned about the window size 5 being seems optimum because any credentials with size less than that yourself is a problem because it's too easy to just simply enumerate all of them, right? What about OS commands? Most of my Linux commands are 2 letters. Does that mean the Windows size 5 is really not good for detecting that kind of injections?
So I haven't run it explicitly on the tracking of OS commands, but certainly in a runtime scenario, you're likely to hook process builder and say, okay, I have some input that came, and is that going out to process builder? And at that point, you're going to have a bash parser that's going, okay, is there ORs here? Is there double ampersand here? Is there a semicolon here? And that should divide it into your various segments. So yes, the chances that someone's going to say curl is likely to get through. If someone's like curl this specific bit.ly link following it, by the time that they're doing something particularly malicious, it tends to get large enough that you're going to see something. I mean, what's the worst you could do in 5 characters? RM, RF star? Like, how much damage could that do?
Yeah, and just to add to that, the technique here is one of many that you can add to this. So if for commands, for instance, you could do a simple parsing to like break up what the segments are, similar with SQL as well. And then you can then treat the segments differently, and it's not just a simple windowed subsearch matching, but windowed subsearch is a one one technique. And what we found is usually what you need to do is have an ensemble. And when you have an ensemble set of techniques, then that produces the fidelity that you want. The key thing around this is that we aren't, by assuming that we cannot trace everything all the time, then that opens up our thought process to think of, okay, assume that you can't know everything. What can you do to fill in the gaps and do that sort of detection? And so it doesn't preclude us instrumenting several points in between. Rather than just 2, we could do 3 or 4 if we know something about the inside. So that could be more like gray box rather than black box. But nonetheless, the idea is that we don't make the assumption that we have a taint that's guaranteed from one end to the other. We assume that that's not possible, and then take the approach of making things work without that assumption, which we find is more promising. Any other questions? Okay, great. Well, really appreciate. Oh, one.
Great, thank you
Okay.
to our speakers.
Okay. Thank you.